9 a.m. I think I'll give you some interesting story about what is going on in simple things like water heaters. In principle, water heaters are as simple as they can be, but when it becomes, when it is a heat pump water heater, then there is some differences than a normal water heater. So I want to talk about the operation of residential water heater. And I'd like to acknowledge here two of my graduate students, Vanjali, who was, before it's she, and they have been working on two models of these water heaters, so I'll try to kind of mix them together both. I'd like to talk in this presentation about facility and conditions that these heat pump water heaters operate, and then full operation. That means to warm up, first start, and then recovery. That means when the water is warmed up and then you use at a different rate and draw that hot water for showering or whatever else is needed. And then I'll show you that recovery performance test or efficiency and compare that to COP, which is on the refrigerant side, and I'll tell you a little bit more what that is. I'll summarize this part of presentation, and then I'll give you in 3-4 slides some information about very interesting, in my mind, modeling of that system, because the system has two very different parts. One is refrigeration system, and the other one is water tank. And you will see now, hearing that there won't be a second speaker as announced in your schedules. I may tell you something more about oil and refrigerant charge and migration over this 5-hour period, because the concern is whether oil is returning well from the condenser. Okay, first of all, I'll tell you something about the performance test, and that, as I already said, and I will be talking about US type of heat pump water heater. Why am I saying US type? Because we are very familiar with Japanese type, which is EcoCute on the right side over here. You don't see that. They should. Okay, that is a Japanese style like EcoCute, which is more appropriate for Japanese usage and their applications, their homes and apartments mostly, and sometimes houses. US water heaters are a little bit different even than Europeans, because the houses are bigger, and typical US heat pump water heater is as presented over here on the left side, with a green and blue cap, different manufacturers. On the top in that green or blue is a refrigeration unit with the evaporator on the top and the compressor. Condenser is wrapped around the tank. And design is made in such a way to be an easy replacement for current, equally sized, equally shaped heat pump water heaters. These heat pump water heaters are selling pretty well in US. Their price is dropping down dramatically. Unlike, for instance, Japanese EcoQs that are going between $3,000 and $4,000 US. US systems get started around $1,500 US and now around $800 US per piece. It is also difficult, still difficult to compete, because the cost of water heater, gas water heater or electricals are a little bit less expensive. You pay around $250 to $300 a piece. So you see that heat pump is still very expensive, yet COP, you will see, is about 3. And some places like California are banning everything that has a lower COP than 1. Now there is another competition to vapor compression heat pump water heater, and that is absorption gas heater, because they can make COP slightly bigger than 1. But then you pay much less for the gas than you would pay for electrical energy, and price, we will see how will that go. Anyway, too many words. So what you see here in this slide is, let me, okay, I'll try to activate this laser pointer in a presentation. I'll try to activate this laser point in the presentation. What you see here is that heat pump water heater attached to the in the loop. And this here is where evaporator and compressor is, and this here is a small wind tunnel to measure airflow rate over the evaporator. This is a schematic of that, what I'm talking about. Compressor is here. It pushes a discharge into 2 branches, 2 spiral coils with a variable pitch to adjust for the heating. And then liquid is going here. It is going through electronic expansion valve. Of course, we have added here mass flow meter so that we measure the flow rate. And then it comes to the evaporator. And that evaporator over here is, after the evaporator, there is a fan, and it goes through a small wind tunnel to measure the airflow rate of the fan. This whole system is placed in environmental chamber. An environmental chamber is, according to ASHRAE standard 72 for display cases, so very uniform flow downwards. And here you have some information about the typical test condition. 25 ambient temperature, that means in this environmental chamber. Initial water temperature 25. Water added during the draw 25 degrees C. Warm up, you will see it's around 5 hours. Standby duration is 15 minutes, and so on. So, in this tank we have placed several thermocouples inside the tank, and the location of these thermocouples are here presented with these dots. At 2 horizontal levels, up and down, and then in 1 vertical level that goes all the way vertically up to measure the temperatures in warm-up period and see what is going on. You will see at the end what is the objective. And this is a location of a sensor, bottom, and sensor at the top, and heater elements that are used for different application, and that is when heat pump is not enough, then just the heater elements can boost the performance if there is not enough hot water. Nevertheless, this is here 250 liters, 66 gallons of water in this tank. For European circumstances, this is gigantic water heater. Typical is, if it is very small, it is as small as maybe 10 liters, 10 liters, or up to 80 liters, depends on application. So here we are talking like everything in the States is bigger than anywhere. Although Japanese EcoCute has a bigger tank than this, but the capacity is much, much higher. Capacity of the compressor and heat pump system. So this slide gives you information about the kind of, we call it full operation. This is water temperature, and we start from cold water, total cold water, and in over 5 hours, around roughly 5 hours, there is a warm-up. And then this is this first period from cold, blue, to almost hot water at 55 degrees C. And then we have standby, and then we have a draw. So somebody is going and taking a shower. And you will see that these experiments that we have done, these measurements, are for different quantity of water that is taken out and different rates. Like some people like to have a very strong jet, some people don't. And some people like to stay longer and enjoy in hot water or whatever, singing in the bathroom, and they spend a little bit more water. So this would be a longer duration, slower draw. And then after that, we have a warm-up. After that recovery, we have a warm-up. So this here at the bottom, let me try to leave this because it's easier for me to watch because it is far from there. So basically what you see here is a power in that period. Typically, energy that is taken from the air drops, as you see here, in time. And this here is energy from the compressor. Power to the compressor goes up. The reason why power to the compressor goes up is that temperature of condensation is going up as you warm up your water. And then, of course, when the temperature is reached, there is no power used. And then the same situation is here, warming up from whatever point was after the warm-up to the point that is required by the end of the process. Here is the actual temperature with the full operation at 30 gallons draw. That means 140 liters is used for something, let's say for a big, hefty shower. So for European applications, you could spend more than a full European-sized 80-liter size heat pump, water heater. And then this here is a drop in temperature when fresh water is replacing that warm water that is being taken for the shower, and this is recovery period. So here we follow with the red is capacity of the condenser. So on the condenser side, as you see, this capacity is almost constant, horizontal. That is the reason why this line of temperature is almost linear. Now, you see here that with this green, it is COP. Basically, COP is going down, and COP is going down because capacity of the compressor, the power input here, is going up because of change in temperatures. I will later show you how pH diagram looks in this situation. So, what is interesting is to see how similar is this COP in a real operation after water is being taken compared to warm-up. And the most important in this particular situation will be to learn, does the way how we take water from the tank affects the performance? And I'll tell you at the end why is that important. You see that I don't. Excuse me, something's wrong with my... Okay. Something's wrong. It will be okay. PowerPoint is not responding. I apologize for the problem. Maybe it is making its automatic backup.
Bill Gates will expect.
They want to, yes, okay, good. So these are the temperature profiles as we were talking about. This is temperature of condensation. These are the temperatures in the middle of a water tank. And this is temperature of subcooling. That's also very interesting because condenser is extremely long. And look at this very interesting situation. Temperature of condensation is going up. Water is going up, but subcooling is also going up. Maybe you would expect that subcooling is going down. On the contrary, subcooling in the system, that means subcooling of the liquid, the different temperature difference between liquid refrigerant leaving condenser and saturation temperature is becoming bigger and bigger and bigger. Okay, and here we have, this is in the warm-up, and the same thing is in recovery, even more pronounced. Okay, let me now introduce two parameters to kind of gauge the performance of the system. And the motivation is after a certain amount of hot water has been used and replaced with the cold water at a certain rate, how much electricity will be taken by a heat pump water heater to bring the water back. And really compare that, which is on a water side measured, to what on a refrigerant side we measured. And this is that heat recovery. This is energy in the water that is delivered at the outlet. That means how much energy have we taken with hot water, compared to electricity input at the same time to the compressor and to auxiliary power. COP of the system is defined on the refrigerant side. That means condensing capacity. In principle, all that condensing capacity goes into water, divided by electricity input by the same input. In theory, these two should be the same. In reality, they are not, because water side differs because non-uniformities of water temperature inside the tank. And I'll show you the data for several tests here. First four that you see is a constant draw, that means constant quantity of water at different rates, at the rates of 25 grams per second to 200 grams per second. This is a lot of water. You probably don't know what that means because you have not been measuring how much water you spend when you take water for shower, because you were not building that. But normal, this here 65 is very good, hefty stream of water. So that is just kind of, normal would be somewhere here. If you are making a shower for the airplanes, as in some of good airplanes that I don't take, these good first class, good airplanes, they have showers, and they are going far less than 10 grams per second, maybe 2.5 to spray in a mist almost, that water to save. But normally we would be here somewhere around 63. So now, when we look into draw, this here is the smallest draw, let's say 56 liters. That's a lot of water. 250, this is to empty an entire tank. I don't think that anybody is taking that much for the shower, but let's say you could use that for 3 showers or something like that. Whatever, morning, and you have daughters. And then there will be, sorry, some of us spend more hot water than the others. So that would be maybe the application. Now, what is happening? This is a typical profile of water temperature at the different locations. So this dark blue is the lowest location. This here is dark blue. This red is the top location. So you see, the colors follow really the temperature or location. So coldest is, of course, blue, and the hottest, which is on the top, is red. So spreading of these temperature profiles means how much mixing do you have during the draw of water from that system. So this here is draw, and this here is recovery. And look what is happening, very interesting, and this is at 40 gallons or 150 liters total draw at 126 grams per second flow rate of water that is being taken. What is interesting here is that the top here is almost not affected at all. It is a red and a constant temperature here, and then you have a little bit effect somewhere here at the top, and this what is cold, it takes a very long time to recover. Why is that so? Because think about what's happening. Your condenser is here around. You have supplied cold water at the bottom, and then that condenser, when system starts to run, is heating walls. So it will be heating kind of uniformly. That means the most will be affected somewhere in the middle as Now we are all smart when we have data. This here shows how temperature is going up relatively fast. This is relatively cold because there are not that many circuits of the condenser pipe, while really the effect of buoyancy, natural rays of hot water is relatively small in this period of time. So, now this is what you will see that, but now, in the next, sorry, we decided again to apologize, to make a, okay, hopefully now it will go. Oh, hopefully now it will go. No. It is, you don't see that it is auto-saving because file is relatively big. Okay, this is the next slide, which now, after this, what we have seen in the previous, with explanations of what each of these charts means, now this is the situation of various quantity of water that is being taken from 30 gallon all the way to 66 gallon. I'm sorry, I thought I will be able to easily modify that to SI units, but it was more difficult than I thought last night to make it in SI everywhere. So gallon is 3.785 liters. So you can multiply that by almost 4, and this is in liters. So what we see here, we see that the draw is the same, draw rate is the same, but the quantity of water is different. And of course, recovery takes longer when we replace more water, more hot water with the cold water. So this is how the system works. This is very important because that comes as an input to the refrigeration system. I again have computer is pretty well equipped with RAM memory, but okay, let me see. This was the next slide. These are the results. What do we see here? This here is condensing temperature in different situations. So here you see 30 gallon, and as we are increasing the quantity of draw, the condensing temperature will be lower in warming up. That means efficiency will be higher. Quantity of energy that we need to put in a system is higher, but efficiency will be higher because condensing temperature due to lower water temperature will go up. So this here is COP, instantaneous COP, which is really what refrigeration system sees. And that means you see now that effect of these draws, quantity of water that is being taken makes some difference. This blue cross X is this 66 gallon. More water we take, higher COP we will get in operation, but we will need much more energy because we need to warm up more water. What is very interesting is here is the chart that I wanted to make and to show to you. This is water draw rate, draw in gallons for one draw rate, which is here 63 grams per second, which is very normal and logical. COP here really doesn't change much when it comes into this situation with 50 or 66 gallons, so it has maybe 3% on effect on the COP. Now, when we start changing draw rate, that means when you open more your water flow, that will have a stronger effect on efficiency of the heat pump water heater. Why is that? And you will see that. It is predominantly because when water comes into the heat pump water heater or hot water tank, if you push it or if you take more water faster, cold water that is coming at the bottom is making more and more turbulence. And that will affect more energy and COP. So now, this is the same drawing, and you see now what is happening when the same quantity of water is being taken at different rates. Obviously, you see that it takes much longer to recover for the same water to be put in and warmed up. When that happens after faster exchange of that water, and this is more mixing. So, this is something that is very difficult to change because this is a pattern of a user. Nevertheless, what is very important, I don't have now the data to show you, but we are working on it, if we can try it. What you can do in that situation is to make, let's say, a separator or kind of a sort of a screen at the very bottom of the tank. So when water comes in and you have a screen, you push it slowly, almost in a laminar way upwards, there will be less of a turbulence. What that will do, that will improve the efficiency of the system and reduce energy required. In other words, you can have the same effect at more efficient way if you know how to reduce the mixing, because whatever mixing we have in the water tank is thermodynamically, it is easy to say, we would generate less of irreversibilities in mixing. What that means is we will see either hot or cold walls of the heat pump water heater. So the results, I apologize, now it's almost. It tells me to wait for the program to respond. I apologize, we wait for that. So you will see, okay, this is now the next slide that I wanted to show you. The same format as we had before. So what do you see here? Of course, the lowest temperature of condensing temperature in time is when we have the smallest, or kind of the slowest draw rate of water. If we don't open too much water too quickly, hot water. Now, what that means here, this is pressure, but this is more important. This is COP and eta recovery, almost following each other, for the constant draw, but at different draw rates. Higher draw rate we have, COP, average COP is going down. COP that could be achieved when you open very small, for a very small quantity of hot water, drops from 3.4 that you see here to something like 3. So this is something like 15–14% lower efficiency you have if you have mixing. In other words, with a relatively inexpensive way of building the tank, you can improve the efficiency of the system for 15%. That is the key. And that's what I'm trying to summarize with this red words, the way we put cold water into heat pump water heater matters. So, in 2-3 slides, to take this opportunity to tell you a little bit more, is to show you a new type of modeling that we have developed here. And this is linking the model of a refrigeration system which is relatively fast, which is things are happening fast, and a very slow changing, totally different model for the big water tank. For the water tank, we are using CFD. It is here fluent. And for modeling of a system, refrigeration system, we use here EASE, engineer equation solver, or you can use MATLAB, or any type of equation solver where you model your compressor, condenser, evaporator, every piece of the component, and you would need to link that to that big mass, which is water tank. So this here is a compressor, schematically, that pushes this red is a hot refrigerant to the condenser, and somewhere here in the middle is this water tank. And we'll make a link between these two, and then subcooled liquid is going to electronic expansion valve to go to the evaporator and back to the compressor. In time, this is how pH diagram presents the operation of the system. The blue is after 5 minutes, then the light blue 30 minutes, 1 hour, 2 hours, 3 hours, and at the end this one here is 5 hours. What do we see? First of all, evaporation temperature is almost unchanged. That is very logical because that evaporation temperature is a consequence of air that is flowing over the evaporator. So evaporation temperature almost doesn't change at all. That means we are less or more taking the same quantity of heat from air and putting it into condenser, that means in water. While condensing temperature goes up dramatically as water temperature goes up as we heat up the water. So this is modeled with the EASE model, refrigeration model. Every of the components is very conventionally modeled. And also, this is relatively conventionally modeled water tank. And this is result of this here. And you see here the velocity due to buoyancy. And the heating is provided here on the walls. The lowest temperature is here, and heating is happening, as I said, at the wall. And symmetrically, axisymmetrically, we have a buoyancy going up. And then cold water is going through the center, and we have almost like a torus circulation of water here. What is the most interesting is the location of the link between these two things. And that is at the wall of the tank, and this is schematically presented a tube of the condenser. So this tube of the condenser brings hot refrigerant, and that heat, that energy, will be transferred to water here at this wall. So we have, this is in a cross section, so this here is that condenser tube, water hot as being heated on this wall is going up, and basically we have presented this as a fin. This here is this thin fin of the tube, and these two upper part and the lower part are put together, and this is another fin. So here heat is coming into this system from the outside and is being taken out by water over here. So that is the logic of that link. Now the problem is when you put the temperature of this surface into EASE program, then you quickly solve the refrigerant side. When that is done, we get new data, and then we transfer these data to Fluent. And that fluent is really made, fluent model is made in such a way. This here is the mesh, relatively simple mesh. The more difficult part is to allocate actual temperature and actual location of these coils that are going all around that tank. So from refrigerant model from a system, from a condenser, we will know exactly what is the temperature at the wall. And then Fluent is calculating the buoyancy effect inside, and due to that buoyancy and that velocity, heat transfer coefficient due to various velocity will be changed. So this is the way to link these two processes, and we have done a pretty good job, and you will see this here. This here is energy that is being needed, or COP, in time, in here 5 hours, 6 hours. You see that here capacity of the condenser drops a little bit, dots are measured values, and lines are the models. There is no fudging. Of course, we have been trying to make it as good as possible, and this is evaporator performance and the condenser performance by itself. When you look into the system, this is here measured temperature and predicted temperature of water in the tank. You see different temperatures, and these different you have three markers here: triangle, square, and a circle, and they represent location of the water temperature at the bottom, and at the top, and in the middle of the height here, as it's shown, and in different time. So this is as water is going up in its temperature, that means time for the process to happen. So this here is velocity and the temperatures. It works fine. It took us some time to make all of that to work, but it is possible. I'm talking about especially younger people who will be doing, older probably, won't need to make a model themselves, but there are students, there are younger engineers who would like to make a model. It is possible. This is a very unusual way of making the model of the refrigeration system, which is not only refrigeration. This will be like you have something else, some object which interface between refrigeration system and the object is the function of the performance of both of these refrigeration system, and in this here kind of BO number, if you will, for that big tank. With this, I would like to stop. Even I have a second part of the presentation with refrigerant and oil circulation, which I will now leave maybe for the next year, tell you how oil circulates, and we have then measured how much refrigerant at which moment is where, and how much oil is where. In other words, we have tracked exactly oil circulation, refrigerant circulation, and quantity of both of these components everywhere in the system in real time as a function of operating conditions for the particular system, of course. So, works, summary of modeling works well, improvement in linking on the way. It is very difficult for those who are interested, because you need to, at this point we are doing that manually. You calculate CFD, transfer these results to Excel, and then move it into ease and go back and forth. We are working now on better linking, more automatic. So it works fine. This is a linking algorithm, but I won't go too much into details. So for me, very interesting from a modeling point and from a dynamics of unusual system case. For you may be interesting in something like how a water heater and tank behaves linked to the refrigeration system. So So if you have any questions, I would be delighted to answer to those.
Any questions from the floor?
Which refrigerant you use in this
Just a
experiment?
moment.
The question was which refrigerant was used, and it is 134A. We have done similar systems with 1234YF, which is more for exercise rather than real. Nobody will use a very expensive YF. 1234ZEE is another that we are now coming, which makes much more sense. We have done the same with CO2, and I don't have now data right now to present. 134A, this is the correct answer. Yes, please.
Kakva je situacija kad imate ekstremno nisku ambijentalnu temperaturu vazduha i hladnu vodu? Da li ste tu uspjeli nešto da analizirate i kakav ste rezultat dobili?
Very good question. We haven't done that. I could speculate. One of the reasons why electronic expansion valve is here is for that particular purpose. You are shooting right in the target. Oh, the question was, what is the situation when the starting temperature is very low and water is low, air is low? In that situation, the capacity is much higher, density of vapor is much greater, and power that is drawn from the system will go up, and the speed of warm-up will be greater. COP will be greater, but overall energy will go up. But I don't have a data for that. That is a very good point. Like everything, we do first what is easy. And to have a very low temperature, let's say 0 degrees C or something like that, and you have a 0 degrees C air, which is very logical, like you come back after holidays and your house is cold, water is cold, you turn on your heat pump water heater, what happens then in that transient? Don't have a data to show, unfortunately. Sorry. Other questions? I have a notion in the back? No?
Ova slika strujanja što je prikazana, CMD što je rađena.
Aha.
Kolika je bila razlika temperatura hladne vode koja ulazi u bojler i neke srednje u bojler?
The question was, what is the temperature difference between water that is coming in and some average temperature? Let me come here where we have them both. I think this is this here. Water temperature that comes in is 25 degrees C. Water temperature that is going out is 55 degrees C. Local temperatures here are presented in this situation here. And you can see this here, the coldest here is shown like 33, but really didn't go to the very bottom. And the red is 61, yellow here is 55. So this green is something around 40 to 47, 48 degrees C. And that varies. As I said, when you more open your hot water and you push more cold water in, there is more mixing. When you go with a small flow rate, gently in and out, you have almost the piston of isothermal water mass that is moving up. And that is much better from the efficiency point of view.
Hvala.
Molim.
Znači, koliko ja zaključujem, ovdje je bitno kako se rasprostiše mlaz vode koji ulazi u bojler.
Apsolutno, potpuno se upravo.
Hvala. Mi smo to ovdje na ovom objektu imali samo za jedno manje temperature za druge uslove. Na ovoj zgradi.
Absolutely, you're right. And as perfectly said, what you have said is you can extend the finding from this heat pump water heater to any type of a water heater where you are exchanging water at different temperatures. So lower, and whatever you do to make it nice, smooth, slow, will improve the performance of the system.
Thank you.
Sure.
A to se kod solarnih bojlera već radi godinama.
The comment is that that is being used in solar boilers for years. Yeah, I agree. Any other question?
More questions from the floor? Then I have one.
Huh?
If you don't want this turbulence, why don't we put it in place so the water has to move up this way? You know, if you have stepwise.
Oh, certainly. That's a very good point. That would work very fine. I cannot agree more. That's a very good practical option. I have a notion that would maybe cost more. You would need to put more of these baffles than one, but that may be, I may be wrong in that. I 100% agree. That is a very logical solution.
Okay.
Some people have it with more tanks, and they are going from the top of one tank to the bottom of the other tank. That's in principle the same concept, but sometimes expensive. Here is that it's relatively small. And actually what is the tendency in heat pump water heaters is to reduce the size of the tank as much as possible, because the space costs a lot, more materials, more costly. That's why instantaneous hot water heaters with a gas and even some big electrical heaters are very popular.
So the reason for the question is more that in big tanks, water tanks for a couple of thousand of liters, it's much more interesting, and you can afford to put in these to control the flow.
Absolutely, yes.
Okay, if there's no more questions, I suggest that we give Mr. Hrnjak